Hi kids, now we'll be looking into this small topic EMF from current electricity. So yeah, this is from some, I think H.C. Verma. So I'll be just reading out and I'll be stressing on the points where I have to stress. So basically, to maintain a current in metallic wire, you have to continuously inject electrons at one end and remove them from the other, keeping a non-zero electric field in the wire. That you people already know. To do this, you need a special device which is battery. Like we'll see how it functions. For example, you can connect a torch cell to the ends of the wire to maintain the field. This is what we will be doing in our current electricity. Now, what goes inside the cell, which we won't, at least I don't discuss much on it. Typically, you have some chemicals in the cell and two electrodes. You will be having some chemicals and two electrodes. Due to the chemical reactions, particular electronic structure of the electrodes, the positively charged ions are pushed towards one electrode and negatively charged ions are pushed towards the other electrode. So, like because of chemical reaction, these ions will be separated and positive ions will be going on to one electrode and negative ions will be going on to the other electrode. Now, eventually what will happen, this side will become positive plate, this side will become negative plate, and there will be electric field generated because of this accumulation. This situation is schematically shown in figure. Now, yes, because of this there will be accumulation of charges and there will be electric field. So right now there were two kinds of forces. Initially there was because of only chemical reaction, something was happening and charges were moving. Now after that eventually there are charges settled down and because of that electric field is coming into picture. Now the force on charge Q, okay, so basically they are talking about this situation still. This situation which is chemical reaction thing. The force on charge Q for this push comes from the local chemistry of the chemicals. Because of the chemical reaction, this will be happening and like they will be pushed on to the other stuff. Now that force is coming because of only that local chemistry. The force on charge Q for this push comes from local chemistry of the chemicals and the electrodes and cannot be given by equations like F equals to QE. So we can't exactly put it in the form of equation where E may be the overall electric field. Let us call this force the driving force and denote it by FD. Now we are calling that force as driving force. Who is driving that? It is because of that local chemistry thing, right? It is because of the chemical nature of the stuff that is happening. Now charges were driven because of some force which is because of that chemical nature thing. Indeed, when the opposite charges accumulate at the electrodes, they create an overall electric field between the electrodes. They are creating an overall electric field now. This electric field also exerts forces on the ions in the cell. Now ions are separating and they are trying to move. Now on this ion, there was only driving force, but eventually on that ion, there will be driving force trying to drive it in this direction. Apart from that, electric field try to push it in this direction. The force on a given ion due to this field is opposite to the driving force. Driving force is trying to push the charge in this direction. Electric field is trying to push this charge in this direction. Both are in the opposite directions. At equilibrium, the amount of charge accumulates on the electrodes will ensure that now at equilibrium, what does it mean by equilibrium? No more further accumulation is happening. Why no more further accumulation will happen? Initially driving force will be more, there is no electric field, but eventually electric field is keeping on increasing and increasing its force, and when they become equal, it is going to become equilibrium situation, right? So in equilibrium situation, what will happen? Net force on the charge is going to be zero. So magnitude wise driving force should be same as electrostatic force on this thing, or vector wise it is FD bar plus Q into E bar should be 0. FD bar plus Q into E bar should be 0. So when I write it in vector form, FD bar plus Q into E bar should be 0. So when I write it in vector form, it will turn out to be this way. In this case, the overall electric field exerts force on the ions equal and opposite to the driving force and no further accumulation takes place, which we understood. Now, the potential difference between electrodes A and B. The potential difference between electrodes A and B will be given by electrostatic field, that is E. So potential difference will be given by negative of integral E bar dot dl bar, where this is electrostatic, conservative electrostatic field, right? Now, but this is our definition of conservative thing. Potential difference is defined only for conservative forces, so we are defining that. But on the other hand, we will be defining EMF as 1 by Q into work done per unit charge, work done by the driving force per unit charge is called the EMF of the battery, but we have already seen these two, minus E bar is FD by Q. So these two are equal in magnitude, but they make different meaning. Eventually we'll see like they may be different at some situations. So you may wonder that if FD equals to minus QU, what is the difference between these two integrals? Indeed, their values are same in the situation. In this situation we are discussing, but they represent two different physical quantities. What does this represent? Because of the electric field thing. This represents because of the driving force thing. This is because of chemical nature thing. This is because of the electrostatic field developed because of the charges. While FD appears due to chemical reactions, E comes from electrostatic field created in the electrolyte. While FD tries to cause the charge separation, E attempts to reduce it in this particular situation, right? Now, when you connect two terminals, current starts in the wire because of the charges accumulated. Now, till now battery thing we have seen. Now, once you connect the terminals, what will happen? We have already seen charges were accumulated. Positive charge was accumulated here, negative charge was accumulated here. Now, what will happen when you connect? This negative charges will flow this way. So, we will call by definition the current is in this direction, right? When you connect two terminals of torch cell by a metallic wire, a current starts in the wire because of the charges accumulated at the electrodes. Electric fields are set up in the wire. Because of these charges, electric field will be set up in the wire, and some charges will appear also on the surface of the wire, which we will see later, but which we don't bother much about that. And finally, steady state will be achieved, and you have a steady electric field E of constant magnitude appearing in the entire wire. Now, because of this positive charge and negative charge, there will be constant magnitude electric field developed here. Now, in that process, there will be some charges accumulated here and there on the surface also. The wire draws electrons from the negative terminal. Wire draws the electrons from the negative terminal and deposits on the positive terminal. So, what is happening? These electrons are going and getting deposited here. Then what will happen? Now, the concentration will reduce here, so the electric field will reduce here. If the electric field reduces, then the driving force is more, so it will try to push the charges here and there. So that's kind of continuously happening. Anyway, we'll see the explanation. Yes, this would cause this would have decreased the concentration of the charge of the electrodes, but the driving force brings these electrons back to the negative electrode to ensure equilibrium in the cell. So what we understood? When you connect these two by a wire, the electrons will flow this way, the number of electrons will reduce here and positive charges will reduce here. So driving force will become more than electrostatic force. So driving force will try to push more negative charges here or more positive charges here to make it again equilibrium. Now, in some cases, the concentration on the electrodes when a continuous current is drawn from the cell is less than that when no current is drawn. Now that makes sense because when continuously current is getting drawn, we don't see like that equilibrium situation achieved with the same charges, right? So it is in dynamic equilibrium or something like that. Then the electrostatic field E in the cell is reduced from its original value. Original value in the sense when no current. See, in no current situation, both forces will be same, or integral will be going to be same. According to the potential difference definition, it is going to be integral E bar dot dl bar. But EMF definition is going to be the same. This is not going to change. Whether the current flows or doesn't flow, this is not going to change. But when the current is flowing, generally this will be less than. When current is not flowing, these two are equal. When current is flowing, most of the times this will be less than this. So EMF and potential difference are not the same things. In fact, this is coming because of the chemical nature thing, and this is coming because of the charges getting accumulated. If EMF and the potential difference between the terminals of the battery remains same, even when the currents are drawn from it, we call it as ideal cell or ideal battery. If the EMF and potential difference are same across the battery, even when the current is flowing, we call that as ideal battery, which we already know. Okay, in the example taken, driving force was confined to a particular portion which is inside the cell of the circuit. In some cases, driving force may be generated throughout the circuit, what you will see in EMI. We shall discuss induced EMF in one of the chapters later, that is EMI, in a situation where the driving force will be of this type. You can define EMF for the whole circuit. Now, we are defining EMF only inside the cell, right? Now, when it is continuously happening for the overall loop, we will be defining EMF for the overall loop is 1 by Q into, whatever, work done for work done per unit charge for a closed loop. This integration can be is to be taken at the same instant of time. If different segments of the circuit, in different segments of the circuit, you have to calculate in FD into DL and add the values, integral and divide by Q. The whole purpose of this discussion is to emphasize that there are two kinds of forces on charged particles in the circuit. One is due to overall electric field produced by the charge accumulation at the surface of the conductor or the electrodes of the cell or anywhere else. Another is driving force, which has its origin somewhere like chemical reaction or some other mechanism. In this situation, it is chemical reaction, but in case of induced electric field, EMI, so that is induced electric field, or like motional EMF, it is magnetic field thing, right? So driving force in EMI will be of two reasons. One is motional EMF, that is because of magnetic field. One is induced electric field, that is time varying magnetic field will produce induced electric field. So in EMI, the driving force will be because of two reasons. One is magnetic force, one is non-conservative electric field. Here it is chemical reaction thing. You should be able to distinguish between these two. The EMF is related to driving force and the potential difference is related to electrostatic force. This is kind of important. Indeed, both have the same unit, volt. We have been using the abbreviation EMF for quite some time without telling the full form of intentionally. Okay, the full form of EMF is the electromotive force. However, it is not really a force. As you can now realize, it is related to driving force through the equation. Remembering it as electromotive force can create some confusion, so we don't have to bother about that. EMF, we talk it as EMF. So essentially what you need to understand, driving force is different, driving force origin is different, and electric field origin is different. So you need to understand there are two kinds of things here, right? Thank you.